thing I can do today is maybe try and prepare you for what you're going to see in the next couple of days of this event. Um, from a theoretical perspective or from the core ideas that I'm going to talk about today, I don't think I have anything new to offer you. I guess most of you are third or fourth year students, right? How many first years? Okay, great. Okay, good. So at least half my slides are going to be educative, right? All right. So you are going to be encountering, and I know that keynotes typically don't do this, but since there are not too many of us, I think we are about 100 of us. So I guess let's make this interactive. Feel free to interrupt me. Feel free to ask any questions at any time. We don't necessarily have to have a dedicated Q&A slot at the end. So yeah, what you're going to listen to over the next 2 days are a bunch of different ideas, opinions, facts, and so on. So what I'm going to do now is try and inculcate some sort of skepticism in you first, right? And why? Why I'm starting with skepticism, that is something that's going to become clear very soon, right? And essentially, if you want to make the best of not only this summit, but other such events or other such ideas that you might encounter out in the industry or in academia, anywhere, a healthy dose of skepticism, especially in a field of AI, where is there a clicker I can use to move the slides, or will you be moving it? Okay, please go to the next slide. So yeah, this is what we are going to talk today. We are essentially going to start by demystifying artificial intelligence. Again, this is a term that unfortunately is very loaded. As we'll find out throughout the course of this keynote, artificial intelligence means many things, of which only a small subset is what we are currently concerned with. And of course, you may choose to, expand beyond that and explore the other avenues as well. But typically, what commonly is known as artificial intelligence today is very different from what artificial intelligence was in the 80s, 90s, and so on, right? So, and typically in fact, I'm not even very comfortable with the term data science. I personally believe that the word data science doesn't really mean anything, right? It's like saying words literature. There can be no science without data, right? So that again is sort of the hint of the kind of skepticism I want you to have. Then we're going to talk about the history and some foundational results in artificial intelligence. This is important again because everything builds on top of it, and these are the roots that you can't afford to forget. These are sort of the checks and balances that help you evaluate an application, or they help you evaluate a particular result in artificial intelligence. Then we're going to talk about what makes an effective data scientist in the industry, right? This is, again, Ketan would probably throw a much brighter light on this. What counts as a effective data scientist, especially somebody who's a fresher, is very different from what typically a fresher is in most other areas, right? And then finally, we're going to talk about what AI means today and what people are doing in the industry with it and how you can be prepared for it, right? But before we begin, I would like to start with an exercise. Can we have the next slide? Okay, let me give you what the next slide is. Please open your favorite news app on your phone and search for artificial intelligence. Take the next 30 seconds to do this maybe. Just look at the search results. What kind of news do you see? Just the headlines. Would anybody like to volunteer an answer maybe? Just maybe shout out a few phrases that you see in the headlines. Anyone? Go ahead, just yell. What are By the way, don't Google search it. Search the news. News is specific. Don't do a Google search. Go on. Hypothetical bioweapon in 6 hours. Great. More. Anything else? All right. Very neutral sounding. Anything else? Let's take a third category maybe. So we've heard two types essentially. Please. No, you got that result when you search for artificial intelligence. Okay, well, recommendations aren't the point. Search for artificial intelligence related news is what I was talking about. Anyway, let me show you what I got when I was making these slides when I did the same exercise. Can we have the next slide? So look at this. Can artificial intelligence boost the pace of India's judicial systems? It gets scarier and scarier. Invents 40,000 chemical weapons in just 6 hours. Is this something similar to what one of you said, right? And Karnataka unveils AI and robotics technology park. So what impression does this give you? There are either opportunities or threats, at least the way people are reporting about it, right? How many of these titles or do you think are actually true? Out of, and again, don't necessarily refer to these 4 headlines, but look at what you get. And try to figure out how many of them are fact and how many of them are fiction. What do you think? But these things tend to be extremely exaggerated, right? Massively. And there is a reason for that, because if things were not exaggerated, people wouldn't click on these headlines. So the way we generate content, especially the way if you are in the media and you want to generate content, you don't want to talk about results that are inconclusive. You don't want to talk about things that bear no correlation. Now, statistics, we have known from a very long time that correlation is not causation. But people will imply causation all the time with correlation, right? That's because if you simply say that correlation is observed or no correlation is observed, that's hardly worth reporting. So whenever people want to talk about artificial intelligence, they are not going to tell you that 1,000 experiments failed. They're going to tell you that maybe one experiment succeeded, which probably didn't, right? So this, and why do you think this is important for us as practitioners, as students? Because your colleagues, your clients, your boss, they are all going to be consuming this kind of content, right? This is what reaches the common man, right? And therefore, when they come to you for any kind of work related to AI, they could have unrealistic expectations, right? And managing expectations is a major part of a data scientist's job. In fact, I would pretty much say it's your professional responsibility to make it very clear to stakeholders, whether they be your colleagues, your clients, your boss, whoever it is, even your students perhaps, to separate fact from frictions, to set very realistic expectations about what artificial intelligence can do, cannot do, within what time, right? So that's basically the idea behind this. But let's take a look at what sort of, why this happens, why there is so much hype. So there is a consulting company called Gartner, which releases something called the hype cycle every year, right? And for most of the upcoming technologies, it does separate hype cycle. And if you look at this graph, there is a very, it's a complicated graph, but let me try and take a shot at simplifying it. On the x-axis, you have time, right? Is it visible, by the way? If it's not, please let me know, right? There might be some pieces of text that are not visible, but let me go over the picture generally. On the x-axis, you have time. Like as time progresses, how do the expectations change? The expectations are on the y-axis. And you see that the time axis has been divided into 5 parts. The first is called the innovation trigger, right? This is the period of time where things start, innovation, some critical point is reached. Some major innovation is made. which makes people sort of buy into a particular technology very rapidly. So this would be something like NVIDIA open sources the CUDA architecture. Now everybody can use graphics cards, not for graphics alone, but for general computing. Since they are parallel, therefore you can build neural networks. So that's sort of the innovation trigger, right? The next is the next section of the time axis is called the peak of inflated expectations. Even industry experts realize this, that the peak is of inflated expectations. This is when, because of that trigger, a lot of people start buying into that hype. And once you see, if you look at the maximum of that peak, you'll see that at the top there is Edge AI, followed by AI Maker and Teaching Kits, Deep Neural Network, ASICs, Digital Ethics, Transformers, Decision Intelligence. Most of these are things that are very real and very active areas of research. But the point is that they're associated with this only because, once a particular technology reaches a peak, it starts attracting other technologies around it. So people will be clubbing AI with Bitcoin, with the Internet of Things, and so many other things, right? So they start clustering around each other. And by this time, people have started putting money into that research. They've started putting money into the research and development of products or solutions or whatever it is, right? And the next cycle, obviously, is called the trough of disillusionment. This is when people realize that all the money is basically down the drain, because the expectations were inflated. What we expected did not happen. The prototypes that we saw did not pan out. There are many reasons for that. We'll go into that as well. And now that we know that, things didn't pan out, so now we are disillusioned. Now we are suddenly pulling away from everything and being again very conservative about what sort of things can happen at the cutting edge of any given technology. And then finally, there is the slope of enlightenment and the plateau of productivity. That slope of enlightenment is when you actually realize exactly what works and exactly what doesn't work. This is when you really become mature, right? That's when you realize that, you might have heard senior people talking about these kind of hype cycles have been keeping on coming for a long time. Before AI, there was big data. Before it, there was map reduce and all of that. The world hasn't changed. It's the same thing, right? So that's because many people are on the other side of that wave. They find themselves on the slope of enlightenment, and after that, when they have acquired a lot of maturity and they have become disciplined practitioners, that's when there is a plateau of productivity. That's when you have sort of maxed out, that we perfectly know how to make use of AI or a particular hype. So reading this hype cycle, again, is something which is important, which you can use to, discern whether something is just fluff or whether it's something actually useful, something meaningful. And by the way, this I'm talking only from the perspective of consumable AI. R&D and academic research is a completely different thing. Sky is the limit there. Go ahead. Right. Let's have the next slide. But again, let me emphasize the point that the public discourse on AI is something that needs to be looked at very carefully. What the media or the common man is going to, speak in terms of AI. I'm terribly sorry about that. Yeah. So here's the thing. Again, before we proceed further, this is one more disambiguation I'd like to make. Mostly nowadays when people say AI, they typically mean deep learning. But that's not what it is. Artificial intelligence is a fairly large area. There are lots of things inside it. There is something called symbolic AI, there is something called linguistic AI, there is something called connectionist AI. So within connectionist AI is this paradigm of neural networks, right? And again, a subset of artificial intelligence is machine learning. A subset of that is neural networks. And one type of neural networks are called deep neural networks. So you see that when people usually say AI, they mean neural networks and actually just deep neural networks. But the word actually corresponds to so many other things. So this is also something that, trips up a lot of people because if you really max out a particular neural network and then people come to you and say, this is not really AI, this is just statistics, then you would probably need to have an answer to that, right? So this is what we mean. And today, for the rest of the session, I'm going to be using these terms interchangeably. You are going to be using these terms interchangeably as well. But do bear in mind what we mean when we say AI or machine learning or statistical learning or anything like that. It's essentially just you know, these four topics. And as long as we understand where they are relative to each other, and we know what part of discourse you are concerned with, what part of an academic discipline you are concerned with, right? Let's have the next slide. So let's talk about why there is all of this talk about AI. Why is it that people are suddenly, you know, writing science fiction and selling it as news, right? So the first primary concept here is that of metric spaces. Why do neural networks work? Why does machine learning essentially work? The first idea is that of metric spaces. Metric means measuring, right? So you have data and you project it into a space where things can be measured, where the data can be measured relative to each other. That's what we call by metric spaces. And the other thing we understand very well is geometry, right? So once we understand the geometry of a particular metric space, we can manipulate that space or transform it into so many different ways, and therefore, you know, extract any sort of results from it, right? So let's take a simple example. Next slide. Let's say you have a bunch of emails and you want to classify them as ham or spam. Simple spam filtering. This is something that is a very common, it's a very easy exercise. It's a simple exercise. That's the sort of, I promise you, you will build at least one spam filter by the time you leave this college, right? At least one. So let's say that there are certain words that we identify as spammy words, right? And those are, you know, look at the bottom of the x-axis. Cash, claim, contact, free, mobile, win, jackpot, those sort of things, right? Offer, you have won. Or, you know, why don't you just go to your spam filter and, you know, figure out some of the typically spammy words. They could also be things like, you know, some ancestor of yours has, you know, left you so much money, please click here to claim that prize and all that, right? So those sort of things are typical spammy words. At the same time, if you look at what are the non-spam words, then you see there are things like buy, care, love, really, thanks, wish. These are very human words. They relate a lot to emotions, right? The others are very material words. They're asking you to do something. Click here, claim your prize. The other words are communicating feelings, right? So in general, I mean, even without using a specific spam filter, it's very easy for anybody to say, create a list of words that typically belong in a spam email and another list of words which typically belong in non-spam emails. And these are not necessarily disjoint sets, by the way. There could be overlaps. But we're assuming that the overlap is not so significant that, you know, the two different sets of words become more or less identical, right? And let's see, how does this help us really to classify hams from spam? Now, every single green circle that you see there and every single red cross that you see on that plot is one email. You take an email, you count how many words from the spam list are in that email. That's your x-axis, coordinate, the x-coordinate. And you take how many words from the ham corpus are there in your email. That's your y-coordinate, right? If I have the x and y coordinate, what can I do? I can plot that point, right? So every point represents one email. What we've done here is that we have taken text data, split it into words, and by doing some operations on the words, we have converted emails into points in a two-dimensional space. What is the advantage of that? Why did we have to go from text to a geometrical space? Feel free to yell, please. Because now we can do maths with this, right? Like now we can do geometry with this. Simple as that, right? So if I get a bunch of annotated data where somebody says that, okay, these are spam emails, these are ham emails, and I plot them like this. Everything that is a cross is a spam. Everything that is a green circle is not a spam email, right? And of course, there is, you see that there is actually an anomaly there. There is an email which has exactly the same number of spam words and exactly the same number of ham words as a non-spam email. So there is one outlier over there. Nevertheless, how do we classify these two patterns now? I'm sorry, is there, Is my voice audible or is there a lot of noise? Because I seem to be getting some feedback. Okay. So how do we classify ham from spam given this representation? Now that we have these points plotted, now that we have figured out a way to convert text into vectors, right? Given data set, we have this plot. How do we classify ham from spam?
We can separate them by creating a linear decision boundary.
Exactly. Next slide, please. That's exactly what you have to do, right? What is on one side of this line is spam, what is on the other side is not spam, right? This is all there is to it. All of machine learning is just this. Of course, the catch there is that not all data sets are as simple as this, and finding that separating line is not as easy as this case. But essentially, this is the problem. Regardless of what anybody tells you, machine learning and artificial intelligence ultimately boils down to curve fitting. The formal name for that is what we call function approximation, right? This is a straight line. How many parameters do we need in order to establish a straight line? In order to draw a straight line, how many parameters do we need? How many unknowns do we need to figure out? Only two, slope and intercept, right? That's all. But what if we had to draw a curve? And of course, we are lucky that there is a straight line which solves this problem. It's quite possible. And in fact, if you think about it, a straight line won't solve this problem because there is one spam email which is on the other side. But let's say we can tolerate a little bit of error, right? You see that point somewhere around 1 on the x-axis and 5 on the y-axis? Do you see that? That's 2 points that have exactly the same signature in our metric space. Classifying them is impossible because, there is no transformation or no manipulation I can do of that data set which can actually render that point classifiable, right? But anyway, this is the idea. Linear separability is the fundamental building block of at least what we know as the classification problems in machine learning and therefore in neural networks and therefore in artificial intelligence. The other class of problems we deal with are called regression problems. There it's even easier because regression is literally curve fitting. You are trying to figure out what the function is that will actually fit a bunch of lines. So that's pretty much it. All of what we are going to study for the next 4 years boils down to solving this one problem for a given data set. The catch, of course, being that not all data sets are that easy. And of course, straight lines or even simple polynomials may not be enough to give you something meaningful. These things can get really, really complicated. In most cases, you can't see them. Right? In fact, if you can see them, and that makes sense because if you could see data, you would just plot it and draw a line, right? Even with hand. Why would you need machine learning? You wouldn't need that. So most interesting problems in machine learning obviously are those that have high dimensional data. You can't visualize them, and therefore you need to resort to a lot of mathematical formalism. Next slide, please. So why is linear separability important? Because it is at the very foundation of what we know as the Rosenblatt's perceptron machine. So if you look at this picture, this person is called Frank Rosenblatt. You probably have encountered. Who has studied perceptrons before? All right. So a perceptron is the simplest possible neural network. It's just a single computational unit. It just computes a dot product and nothing else, right? And it has some very interesting properties. Let's say that in our ham and spam example, you had two features, x1 and x2. x1 was, say, the x-axis, number of ham words, number of spam words. Let's say that we had three features, x1, x2, and x3 for every data point. Then there are certain weights associated with it. And that sigma that you see here is some operation, some thresholding or activation operation or something like that. Has somebody studied logistic regression yet? Okay, so this is very closely related to that. And the way the training algorithm for the perceptron works is that it sort of it gives us guarantees about linear separabilities. Like if your data actually happens to be linearly separable, a perceptron will definitely find the correct solution in finite steps, right? And if you think about it, that was remarkable. So next slide, please. That machine we saw in the earlier slide was actually the very first neural network ever built. So you see that there are, let's say, two different class of problems you're solving. On the left-hand side, you'll see that there are two classes with a nice big gap between them, right? So I can draw a line and separate them. And as long as that gap exists, a perceptron is something that will be able to find it. You don't even need to plot it or anything like that. You don't have to do any analysis. You do not have to assume any sort of properties or distributions or any statistics about your data. If there is a gap, the perceptron will find it. In fact, this can be so conclusively proven mathematically that you can use perceptron simply to determine whether a data is linearly separable or not, right? What if you have more than two classes? What if you want to separate between more than two categories? Well, use more than one perceptron, right? So if you have three, use two perceptrons, because then you'll be able to draw two lines and shatter the space into multiple regions, right? Next slide, please. And here's the thing that, again, I'm reiterating this, that if the classes happen to be linearly separable, if the patterns that you're trying to classify have a gap between them through which a straight line can pass, the perceptron will 100% find it. This is a guarantee. This machine came out, I think, in the late 40s or the early 50s. And when an algorithm like this comes out and it says that, we can guarantee linear separability, what kind of reaction do you think people had to that? Note that this was a time when there was no machine learning. People used to mostly rely on higher order statistics at best, which, by the way, was still pretty powerful. But at the same time, statistics meant that you had to make a lot of assumptions about your data. This was the first truly, self or a truly supervised learning kind of a problem. They say that as long as there is a gap, we'll find it. This was unprecedented. What sort of reaction do you think people had to that? In the time when neural networks don't exist, in the time when, even forget about neural networks, probably the only thing that exists is regression. And somebody tells you that, we can find boundaries automatically. No assumptions, no linear regression, by the way, even that has a lot of assumptions that need to hold before the model actually converges. Obviously, this was unprecedented and this was really, it drove people crazy. Next slide, please. Because this sort of was, this was a kind of guarantee that absolutely nobody had been able to provide. So look at these headlines now. Electronic brain teaches itself. New Navy device learns by doing. Psychologist shows embryo of computer. Embryo of computer, by the way. Look at the words and the phrasing there. Designed to read and grow wiser. The article on the right, the design of an intelligent automaton, and let me read out the fine print for you. Introducing the perceptron, a machine which senses, recognizes, remembers, and responds like the human mind. Written by none other than Frank Rosenblatt himself. Do you see the connection now? These articles are from the 50s. What do you think about this? I for the life of me cannot figure out why Rosenblatt would write such an article, because you look at the words he's using. He's talking about a machine which senses, recognizes, remembers, and responds like the human mind. That's a far stretch. A perceptron is one tiny neuron. With a billion other neurons, you wouldn't be able to build something remotely close to a human brain. So we've only been talking about hype the way we see it, but this happened back then, and I don't think the headlines have changed much. This was the trigger of innovation, right? And of course, look at the headlines again. Electronic brain teaches itself, it's not a brain. And it, well, teaches itself is probably true, Psychologists show embryo of computer designed to read and grow wiser. Again, these are extremely highly inflated claims. And so the idea is that, people sometimes believe that this idea of, hyper marketing or fake news or something. Well, I wouldn't go so far. I wouldn't be so unkind as to call this fake news. But if you think about the way people amplify things, most people think that this is an artifact of the modern age, since media became more accessible, and since, there is big data and getting access to information is easy, and 4G data on your phone is cheap. That's why people have nothing better to do than to just, share links with each other. That's not like that. This has been a problem for 50 years now, right? Hype about AI, essentially. But this did not pan out as planned. Next slide, please. The single biggest strength of the perceptron, which was that guarantee of linear convergence, was also its single biggest weakness. There was this seminal book simply called Perceptrons by Marvin Minsky and Seymour Papert. This came out sometime in the 70s. And what they were trying to do was simply, elaborate on the perceptron and show why it was such a remarkable idea. And by the way, it is still useful. It's not like you wouldn't use it. I see. Have we lost a screen? No problem. So what they were trying to do in that book was simply, propound on that idea more, elaborate on that idea more. But because they had to do that, they had to do a holistic study of the perceptrons. And there they found a bunch of irregularities, or not necessarily even irregularities. The theory behind the perceptron is fairly solid. But they found a lot of very common scenarios and problems in which perceptrons don't work. In fact, the only scenario in which a perceptron works is linearly separable classes, right? And in order to ensure that classes be linearly separable, you have to go to great lengths. For example, in simple case of spam filtering, it's perhaps doable. But let's say you want to build an image classifier where you want to separate a cat from a dog. How would you build a linearly classifiable data set? It's possible. But there's no way to actually do that, right? So then people realize that in order to make the perceptron to work, you have to have what are known as hand-engineered features, right? So for any data set that you're trying to solve, any machine learning problem that you're trying to solve, you have to do the feature engineering yourself. You have to extract exactly the right features, which will project the data into a space that makes it linear, and then I can use the perceptron, right? And this was so expensive that people said, okay, this is, oh, thank you so much. I don't think it's not connecting. Sorry? Oh, sure. Oh, works. So do I have to be standing somewhere for it to work? I just turned the laptop this way maybe. So anyway, while we get connected, this was sort of, we are a few slides ahead. Yeah, there we go. Sorry. Perfect. So there we are. This is why the perceptrons were such a big deal, and because, there is a simple counter example for this. If you think about logic gates, a simple AND gate where, let's say you can always write down the truth table of a logic gate, and 1 is on the x-axis and 0 is on the y-axis. You will see that perceptrons can separate most of them, but the tiniest counter example gives it away, the XOR problem, the exclusive OR problem, which is shown there, see? So the pink dots are the ones of the output of the XOR gate, and the green dots are the zeros of the output of the XOR gate, right? And you want to simply classify this pattern. You want to separate the green dots from the pink dots. Can a perceptron do it? How many of you think a perceptron can solve this problem? A perceptron, by the way. How many of you think a perceptron cannot solve this problem? Why? No linear separability, right? So what can I do with this? A simple XOR problem. I have to hand engineer the features. I have to do some sort of transformation on the data myself so that it becomes linearly separable. One simple way of thinking about this is, let's think of this as a paper and you fold it along this diagonal, right? So then the green points become overlapping and the 2 points, the two red points are where they are. Now I can cut that paper off and there's my linear separability. But I need to know how to do that first, right? And that's a very specific transformation that I just thought of right now. For an arbitrary complex problem, who's going to sit and think about all the transformations that you can do, which will induce linear separability into your data set? There's no guarantees that that will actually work, right? This was the downfall of perceptrons. And because this happened, this paper, this book, while it was trying to study perceptrons and analyze them in more detail, it inadvertently, contributed to what is known as the AI winter. So this is from the Wikipedia article of that book. It is claimed that pessimistic predictions made by the authors were responsible for a change in the direction of research in AI, concentrating efforts on so-called symbolic systems. So then people started thinking of artificial intelligence as something that can manipulate symbols. And that makes sense, because language is simply a manipulation of symbols. Mathematics, arithmetic at least, why arithmetic? Even algebra, in fact, is just a manipulation of symbols, right? So if something can manipulate symbols, it's intelligent. So they started going in that line. There was a linguistic branch because, if somebody can understand languages, and inherently you see languages are very mathematical. For example, if I speak a grammatically incorrect statement, you may not be able to tell exactly what is the grammatical error that I've made, but you'll be able to detect that, right? So, you probably wouldn't go and talk about, say, the formal linguistic error that I've made when I speak something that is grammatically incorrect, but you can instantly tell that, this doesn't sound right. Why does that happen? Because we are good at manipulating symbols. And, it's a good argument that manipulation of symbols is what leads to intelligence or what is intelligence, right? But neural networks fell into what is known as the connectionist paradigm of artificial intelligence, and that sort of completely blacked out. And unfortunately, these other areas also did not show too much more promise. So that in the 1980s was called the AI winter. Not much work happened, nothing much came out. A lot of other parallel things were going on, like what we know today as, say, support vector machines and ensemble models and so on. They became very popular, still very popular, very useful, of course. And also equally important, as important, if not more, than neural networks. And then we come back to the revival of neural networks. Early 2000s, or basically the late 20th century, early 21st century, essentially. The biggest contribution to artificial intelligence today is this paper, multi-layer perceptrons and backpropagation. By the way, backpropagation, has anybody studied neural networks and backpropagation so far? Okay. Great, very good. If you understand this one thing, you're set in neural networks. That's pretty much the only thing that you need to know, right? But okay, I'll probably be a little more frank with you. You don't need to actually know how it works. Andrew Ng himself says that sometimes he doesn't understand how backpropagation works. And by the way this class of algorithms is also called multi-layer perceptrons, which is misleading. These neural networks their trainings have nothing to do with how perceptrons train. Like, it's just a bunch of different perceptron-like devices put together, but their training is very different from what perceptron. And by the way, Geoffrey Hinton, the second from left, this gentleman over here, who basically came up with multi-layer perceptrons and backpropagation, he has actually gone on record and apologized for calling them multi-layer perceptrons. That was kind of his fault, and he said that, I probably should have thought of a better name, right? So they published this paper in 1986, which figured out a systematic way of putting together multiple perceptrons. Now, one perceptron can draw one line, and if you want to draw a curve, you can put together multiple straight lines and approximate that curve, right? Again, function approximation being the central idea of machine learning, right? And if you can do that, you should be able to manage with given enough perceptrons or enough artificial neurons, you should be able to approximate any function. That's the idea, right? And how do you train such a network? With backpropagation. That was essentially the contribution of this paper. The first convolutional neural network came around only 3 years later. So just a while ago when we were talking about, let's say, a cat versus dog image classification problem. How would you extract features from cats versus dogs? If a human were asked to do it, they'll probably look at, say, the shape of the iris of a cat, which looks very different from that of a dog. Or, you know, maybe the tail of a cat looks very different from the tail of most dogs. There are obviously some dogs who look very similar to cats. So there is that tiny overlap, you know, there is always some tiny overlap, but you can tolerate that kind of an error, right? So if you were to sit down and start training data, collecting training data yourself and training the machine yourself, or if you were to say, teach a computer by simply talking to it, you would tell the computer, okay, look at the eyes, look at the tail, look at the fur, and so on. So this is called hand engineering features. You are trying to pull out specific information, right? This is incredibly expensive, right? You can't do that for all problems. Beyond the point, you will run out of things too. Like, for example, I think Ketan this morning was talking about cell counting. So, in fact, I was dealing with this problem recently where we are looking at, say, the slide or a microscopic rendering of a tissue, and you want to figure out which cells are cancerous versus which cells are healthy, right? We know so little about these things that, you know, simply looking at it doesn't make sense. They have to be looked at by an expert, and even the expert probably will not be able to tell you in English what they saw in a particular cell that made them believe that it was a cancerous cell, right? So we can't rely on hand engineered features at all, right? So convolutional neural networks were the first devices that made hand engineering features unnecessary for at least computer vision related problems. Right? Later, of course, the same technologies did get applied to natural language processing and other kind of problems, but the idea was that for at least computer vision related problems, hand engineering should not be required. So that was one major jump again, and because those convolutional neural networks, CNNs as they are called, they were also trained again with backpropagation itself. So you see that there was a strong result, then another major result building on top of it. CUDA becomes open source in 2007. And again, this is remarkable. A major company who's probably the only monopoly in that space. I doubt if AMD was, well, they were definitely around at the time, but I don't think they were as big as they are now. Today, AMD and NVIDIA are like properly, you know, competing. But in those days, there was very little competition, of course. Like, it was very clear who the monopoly was, and then that monopoly goes ahead and says that you can use our graphics cards for pretty much anything. You just buy the hardware, everything else is free, right? And you make that interface open, right? So CUDA, and again, why are graphics cards even important? Because of parallel processing. You'll see that the very nature of neural networks is such that computations can happen in parallel. They don't depend on each other, right? And you have all of these cores which can just do a lot of work in parallel. That's incredibly fast, very useful. And these are computationally extremely expensive problems, right? And then again, something of, this is debatable, but I do believe that it is representative of the kind of thing that we saw. In 2012, Coursera was launched. And it launched with 2 courses. Both of them were being offered by the founders of Coursera. I forget the name of the person who used to teach probabilistic graphical models. Ketan, do you remember who was the co-founder of Coursera? Andrew Ng and? Right. So she was teaching PGM, probabilistic graphical. Oh, you're looking it up. Thank you. So, yeah. So Coursera, at that time, obviously, nobody knew what it was going to end up being, and it started with these 2 courses, probabilistic graphical models and machine learnings. A lot of people took that course, and when people took that course, people knew what machine learning was. But at that time, it was the domain of extremely highly qualified academic people. It was not something that everybody could do. But when they took that course, they realized that, oh, this is machine learning. Okay, now I can do it, right? Daphne College. Yes, right. So, and again, both very core mathematical data science subjects. So Coursera started its journey with those things. So, and what that course in machine learning did was that it brought a lot of amateurs into the field of practicing machine learning people. In fact, I remember that even at the time, the course was being offered in MATLAB. Octave, yeah, same thing. But anyway, I mean, at least you had access to Octave. Today it's down in Python, so you see what's happening, right? But that's why I say that that particular the MOOC, the first machine learning MOOC that came out, was a turning point because a lot of people started gaining confidence after that. They realized that this is not magic. This is not. It's just essentially linear algebra, calculus, probability, and statistics. There's nothing magical about this, right? So that is why people got the confidence to sort of run machine learning on their own, study it on their own, even do research on their own. So people like Jeremy Howard, for example, they have been promoting this idea for a very long time that you don't really need to be a PhD in one particular subject to be able to do research in that area. How long it takes for people to take it seriously, that's another story. That's entirely up to you. So there we go. You know, CUDA becomes open source. And again, like I mentioned earlier, it was earlier programmable only in C. And typically people who are good machine learning people are bad programmers. This at least was the case a few years ago. Hopefully things are changing now. Which means that anybody who, and again, like, you know, when we were studying machine learning in college, MATLAB was the only thing we had. There was absolute, anyway, MATLAB was the only thing installed in the labs in the electrical, or maybe LabVIEW or something like that, but you couldn't do machine learning on those kind of things, right? So, and you can't touch CUDA cards without C, at least at that time. Now you have PyTorch, TensorFlow, so many other things. So this is what I meant really. Somebody with a little bit of scripting knowledge can get a lot of things done, right? So this is where the democratization sort of began. In fact, I, um, if I was, you know, trying to be romantic about this, what I would say that these are the people who sort of, they are the Prometheuses of this universe. They stole fire from the gods and gave it to the mortals and so on. But there it is. This, in a nutshell, is why this sort of thing happens, right? All of that history is behind these sort of headlines. So, and again, like I said, most people around you are going to be consuming this kind of content. Why this history lesson was important is because this is what is going to help you identify what sort of problems deep neural networks are good at solving versus what are the kind of problems that they're not good at solving. There are many other paradigms also. There is reinforcement learning. There is also just basic statistical models that can be very useful in so many scenarios, right? So typically what has happened with, because machine learning is cheaper, because neural networks are cheaper, because it's so much easy, what people are doing is they're just throwing neurons at every single computational problem that they get, right? It doesn't necessarily work. In fact, it's quite wasteful most of the times. So you need some sort of a discerning eye, and the history sort of gives you a perspective of where machine learning, or rather deep learning, started, where it failed, and finally why it succeeded. Why is it the de facto standard today? And if you find yourself deviating from those principles, you will probably have a little bell going off in your mind telling you that you're down the wrong path. Right? That was the idea. All right. This is pretty clear. I think I don't need to tell you about the applications of neural networks, but why the slide exists is because if you look at it, those are the only areas where deep learning has sort of completely made its mark. We know that, you know, we can't beat conventional, the conventional models cannot beat deep learning is in text processing, natural language processing, and computer vision. Deep learning probably still can't play a game of decent chess. So these are fuzzy problems, probabilistic problems, problems that humans are very good at. But if you ask a human, how do you solve this problem, they won't be able to tell you. So these typically deep learning models tend to be useful in situations where no specific rules can be extracted from the data. But overall, there is a strategy which cannot be communicated. Because if rules could be extracted, you'd just tell the computer those rules, right? So there we are. Yeah. So quick recap, linear separability, we understand why it's important, and once it's there, what you can do with it, and if it's not there, again, what can you do to induce it? Feature engineering, like I said, you can fold that XOR paper and cut it in half to make sure that it is now linearly separable. Specifically, this particular method is called the kernel method. There are certain functions called kernel functions What they do is that if your data is not separable in its whatever dimension it is in, they project it onto a higher dimension, right? Is there a, okay, I wish we had a blackboard, but anyway, I mean, let's say that there are two concentric circles, the inner circle is one class and the outer circle is one other class. Not exactly concentric circles, but you get the idea, right? We want to separate the inner points from the outer points. Not something a perceptron can solve, again. Well, it could. If you put together 5 perceptrons and made 5, like a pentagon around the inner one, but again, that's not a guarantee, right? Because what if you sample more and more points from the same data set from the same distribution? You get something fully spherical, right? So how do you fix this? You use something called a radial basis function kernel. There are many possible kernel functions, of which we're using one. We just assume that this particular view of that data set is a top-down view. The data is actually conical. It's sort of like a bell. And you're looking at the top of the bell at the center and the bottom of the bell on the outside, right? And if you, now since you're looking at the bell like this, all I have to do is look at the bell like this and I can cut it here, right? So my data was originally in 2 dimensions. I project it onto 3 dimensions. And in those 3 dimensions, it becomes separable, right? This is what is also called the fundamental theorem of statistical learning. There is a very strong mathematical results which proves that with overwhelmingly high probabilities, you can always project lower dimensional data into higher dimensional data. And it will be separable in that higher dimensions. The problem, of course, there is that you have to find the right kernel function. Not everything is, again, as simple as this. So this is another big foundational concept in machine learning called support vector machines. What they do is they put together this concept of kernel functions which project data into a higher dimensions. And like I said, it can be proved with very, very high accuracies and very high probability. There is a proof, a proper mathematical proof, which says that if any data set is not separable in a given dimension, project it into some higher dimension, it's going to be separable there. So you can always go to higher and higher and higher dimensions to ensure that it is separable. Right? So the obvious question is that if we know that higher dimensions my data will always be separable, why do you need anything else? Perceptrons can, once the data is separable, perceptrons can do their job. Right? And in order to make the data separable, I can always use kernel functions. If this is the case, any problem should be solvable, right? Those are the only 2 things we need. So why do we even need neural networks? Any guesses? Okay, first of all, is the question clear? We have talked about 2 results. If linear separability exists, perceptrons can solve it. Guarantee. The second guarantee is that linear separability, if it doesn't exist, can always be generated through kernel functions. If this is the case, which means you put together anything with support vector machines, you should be able to solve pretty much any problem, right? So why do we need anything other than this? Why isn't this the whole and soul of all machine learning or all artificial intelligence? Why do we need anything other than this at all? Any guesses, theories, thoughts?
SVM takes a lot of time to train. Its time complexity ranges from omega of m square n. That's why we don't use generally SVM. We use.
Sorry, what was it takes a lot of time to train and then?
Its time complexity is basically omega of m square n. That's why we don't use SVM.
Neural networks are way more expensive than SVMs.
Yes.
Well, maybe at least not shallow neural networks, but deep ones, yes. Like the smallest convolutional neural network is going to be more expensive than the most extensive SVM.
Okay.
VGGNet has 19 layers, so. Sure, I mean, practically, yes, that is a consideration, but let's say you had infinite compute speed.
Well, it is hard to find the how many number of dimensions you are going to need, and the
Precisely, exactly. You don't always find the right kernel space, right? Are you going to keep plotting that data? And of course, beyond 3 dimensions, you can't see anything. So there is no guarantee that you will be able to find the right kernel functions. In this case, we are using the RBF kernel function. There are linear kernels, there are polynomial kernels. How many polynomials are there? How many polynomials can you write down in a day? Well, Okay, let me rephrase that. How many polynomials exist? This is an easy question, come on. Infinite, right? So, which means that there are infinitely many possible kernel functions, and when you're searching for them, you are searching in a space that is infinitely large, right? Non-solvable problem. So this is again where neural networks come in. So you see, polynomial kernels are only one type of kernels. There are obviously radial basis functions and there are linear methods. But pretty much everything can be approximated as a polynomial. I think even a Gaussian function can be approximated as a polynomial. It's something like, maybe you've studied the Taylor series or the Maclaurin series and something like that, right? So pretty much anything can be approximated with a polynomial. What is so special about polynomials? Because imagine that every coefficient is one neuron in your neural network. Then your neural network essentially represents one polynomial transformation, right? Which means that it's kind of doing the same thing that the kernel method does. Not actually, but it's the mathematical equivalent of that. So instead of, we say that, okay, there is this lower dimensional data which is not separable. We'll project it into higher dimensions using some polynomial kernel, and then we'll draw a straight line around it. Instead of that, we'll just push everything into a neural network. We won't be able to tell it what polynomial to use because it's not actually doing a polynomial search, but it uses its own dynamics to separate the data, and it's the mathematical equivalent of what a kernel would do. Of course, if you have to find more and more such, if your data pattern gets more and more complicated, you add more and more neurons to the neural network, right? But if one layer starts becoming too large, it becomes unmanageable. Your polynomial becomes something with too many coefficients and too many degrees, right? Higher and higher degrees. So if you can't make it wider, what can you do? You can make it deeper. And that is where the word deep learning comes from, right? Because essentially what one layer does is that we won't go from, let's say, the actual data space to the ideal data space, ideal dimension. We'll go there step by step. So that's what they do. Whereas the SVM will try to jump in one step, right? Neural networks, especially deep neural networks, make this task a lot more manageable at the cost of time, at the cost of money, and so on, right? But at least problems become solvable. So this is how you connect something from like as elementary as the perceptron to something as complex as deep neural networks. And again, the reason for all of this theory is when you encounter problems, you need to have a good handle on whether they are solvable at all with a particular strategy or not, right? So there's a summary of this particular session. Neural networks are fundamentally very similar, very simple and very fragile machines. They are very easy to break. They are very easy to corrupt. It's very easy to fool a neural network. There's an entire line of research called adversarial attacks on machine learning models, right? They make many assumptions about themselves, about your data, and they work on a very specific class of problems. That class happens to be very large and it may be the need of the day today, right? We know we need self-driving cars. We know that we need spam filters. We know that we need intelligent cameras that can tell a person's age or something like that. It's a very specific class of problems. But nevertheless, it is just one class of problems, right? So this is why you need to know how to manage expectations with people. What is the type of things that a neural network can do? What is it that it cannot do? Be clear about that. And finally, learn to distinguish fact from fiction, right? That was the idea. So I did have a bunch of other content, but I'm not sure whether we are doing well on time. Okay, it's almost 12. I think my hour is up. So, but anyway, let me just quickly wrap up the rest of the discussion. I wanted to talk about the effective data scientist, but this is something that we can maybe just skip through or just go through again very quickly. I think again in 2011 or 12, there was an article in the Harvard Business Review which says that this article was written by a person called DJ Patil. Has anybody heard of who DJ Patil is? The man who was behind the term data science. He invented the term data science. He was the chief data scientist of the Obama administration. He is the person who single-handedly turned LinkedIn into a fully data-driven company. So pretty big of an authority. And he claimed in an article in the Harvard Business Review in the 21st century I think it was in 2012 when this article came out. The title of that article was "Data Science is the Sexiest Job of the 21st Century." That has ruined everybody's life because people are just assuming that that is true. And the article was written at a time when 88% of the 21st century had yet to happen, right? So uh, a lot of people read that, a lot of people went with it, and a lot of people just uh, assumed that that was true, but it's not really. It's a lot of sweat, blood, and tears that go into a data science job. And but that's the idea. I mean, the idea is that it's the fashionable view to think of data science as the sexiest job of the 21st century. It's not really. There are many more jobs that are rewarding. Not this is, by the way, not to discourage you again. The idea is to make it very clear what the reality is, right? There are any job can be as rewarding as you want to make it, right? The honest view is that data science doesn't even really mean anything. It's a collection of bunch of different tools and it so happens that the market has started valuing this particular collection of tools in specific individuals, and that's why they've started investing money in it. Because all senior data scientists that you look at today, you'll see that they're all coming from different domains. Because 10 years ago, there was no such thing as data science. So if today somebody is a senior data scientist, they would probably have been a chemical engineer when they started, or they would have been an electrical engineer when they started. And that is kind of the point. Like, it's something that is ubiquitous, something that can be applied everywhere. But that doesn't mean that you can completely replace domain knowledge with data science alone, right? The fashionable view again is that data science is all about artificial intelligence and deep learning. Not true. Most of the time, in fact, I don't think, probably Ketan can correct me if they're wrong. Does there exist a job where you are writing CNNs every day? No, I doubt it. Exactly, right? Nahi hai. Right? So that again, it's a lot of software engineering and it's a lot of applied statistics. Without these two, and you can think about it, because if you want to spend your entire life inside a Jupyter notebook, then you are very easily replaceable. Because it's just a matter of time before somebody who can do a better job at, just residing inside that Jupyter notebook at maybe much less money, right? Is the idea. Correct. So an effective data scientist is someone who knows more statistics than an average computer scientist and more computer science than an average statistician. This is an apt definition, right? Someone who knows linear algebra, calculus, probability and stats, happy to write application codes, and somebody who likes working with databases and file systems and web APIs. This is crucial. Because otherwise you'll spend your life inside a Jupyter notebook or an Excel sheet. Somebody will come along and replace you. If you cannot make your data science consumable, you are very easily replaceable, unfortunately. So do invest skills in the software side of it, in the hacking. Especially, I think, I wouldn't even call it software engineering, but the field is changing so fast and there are new toolkits and libraries coming out every other day. The one thing that you really need to be is a good hacker. And by hacker, I don't mean, the criminal hacker kind of sense. You know what hacking means, right? It's just something which is sort of a tinkering behavior where you are able to read documentation, try something out, break it open and see how it works, right? So that hacker mentality is what we really need. From the theoretical side, it's linear algebra, probability and stats, calculus, programming. And here's the thing, pretty much every engineer studies this. But nobody told me, well, not that they didn't tell me, but when I was studying engineering mathematics, I was not paying attention to this. Nobody was paying attention to the maths part of it. I wanted to go and build circuits. I wanted to do signal processing, right? Conveniently forgetting the fact that math was at the center of all of that. Don't repeat that mistake, please. Pretty much I think even civil engineers study a little bit of programming. Obviously mechanical, they have to, but I'm sure something as removed from programming as civil engineering also has elements of programming in it. So these are things that pretty much everybody studies, but of course, because we don't take them seriously enough at the right time, you have to pay that penalty again. We had to study these things again all over, and then, in retrospect, we started remembering ki, yeah, I've learned this and now I understand what it really means, right? So don't make that mistake again. Okay, this is just a half joke article written by a person called Zed Shaw, who's a pretty big name in the Ruby community. Just like data scientists need to know programming, the same is true for the other people also. Programmers also need to know statistics. And he's talking in terms of quality assurance and everything. You don't have to share his aggression, but it's easy to understand the point he's trying to make. Basically, the story behind this article is that he was asking one of his engineers, what is the probability that a particular release will fail? And we are releasing 100 packages of some Debian distribution of Ruby in a particular month. What is the probability that one of them will fail? Nobody can answer that question. Why can't you answer that question? Go look at the data. Because we already have bug reports coming in. We already have crash reports coming in. This question should be answerable, right? But then it turned out that his software engineers were so bad at statistics that he went on a rant and wrote that article. Would you want to hire a data scientist just to do that? No. So this is something that is, again, I think this is what, second year engineering at best. Maybe even 12th standard, who knows? Right. Okay, I think this you already know. So yeah, this is finally something that I'll leave you with. AI is not inscrutable magic. Hilary Mason, by the way, is the chief data scientist of bit.ly, right? I'm not sure what she's doing nowadays. But there was this thread on Twitter, what's something that seems obvious within your profession, but the general public seems to misunderstand. This is true about AI. It's not inscrutable magic. It's math and data and computer programming made by regular humans who are just people who like math and data and computer programming. That's about it. So I hope that helped. I'm happy to take any questions and I'll be around for a while. Oh, and by the way, let me just skip this over, go right to the end. Yeah, feel free to contact me on these addresses, and we are always hiring. There are a lot of people I know who are always hiring, so do reach out all the time, anytime. Sorry? Oh, the slide is fully visible? Oh, okay, cool. Thank you. Happy to take any questions.
Thank you, sir. I'm sure students have been immensely benefited by your session. And as a token of gratitude, I request Dr. Gopal Sakarkar to present a memento to Mr. Jaidev Deshpande.